in many applications, it would be useful to be able to write down a coordinate system from the perspective of the curve itself. So instead of um, prescribing a particular location as the origin and describing everything else in XYZ coordinates in relation to that origin. Um, for example, if you're designing a roller coaster, for example, it'd be good to be able to describe what's happening to the roller coaster as it goes through the curve itself. How fast is it turning? And well, there's a certain amount of g-force that people can handle. You don't want to go through too quickly through a turn and then have people pass out because the blood rushes to the head or something. So um, let's talk about how this local coordinate system works. And using that, we're going to talk about curvature, how quickly a curve turns. So let's jump to it. Okay. All right. So we've actually already started to talk about these local coordinates already. We talked about what's called the unit tangent vector. Um, so the unit tangent vector is a vector that points in the direction of the motion, but the speed information is gone. Like you divide out by the speed, so you just have one unit vector pointing in the direction of the travel. So we reserve the capital T vector for this type of direction. So that's the first local coordinate vector. Okay, and it's best to think of it as a direction of movement. Okay, the next direction that's important to the motion is the direction in which you are turning. So that's called the unit normal vector. And that's the direction of turning. So how do you compute this? Well, you look at the derivative of the unit tangent vector itself. So unit tangent vector is pointing in the direction of movement, and whichever way it's turning. So if it's turning upward on a roller coaster, that would be the unit normal vector direction. It would be the up direction. And basically, you just take the derivative, and again, you want it to be unit vector. So you divide by the magnitude of the derivative of the tangent vector. Okay. So you have the direction of travel, you have the direction that's turning. What is the third direction? Well, once the first two directions determined, the third direction is determined by the right hand rule. So that's what's called the unit binormal vector, and basically the right hand rule. So you take the cross product of the unit tangent with the unit normal vector, and that points in the third direction that's left in the 3D world that we live in. So T and B forms a local coordinate system. And not only that, it has a coordinate system for every time t that's given in the problem. So as the curve moves, as the particle moves, there's an attached coordinate system that kind of travels along with it. So I want you to imagine you're driving a car and you're going in a parking garage, and it's one of those multi-level parking garage where it kind of goes up in a circle, in a helix, until you get to the floor where the parking isn't full, and then you get off, right? So let's say you're in a car kind of traveling along this helix on a parking garage incline. And let's say you're turning left as you go up this ramp. Okay, so let's say this is your vector function describing your location in the parking garage. And then let's compute the local coordinates for this thing. Okay. So we take a derivative. Okay. And this gives us the direction in the unit tangent, but we have to divide by the magnitude to get it into unit vector. So let's compute the magnitude. Okay. In the first two terms inside of the square root, if we factor out the r squared, we get sine squared plus cosine squared, which is always equal to 1. So the magnitude of this this velocity vector is square root of r squared plus 1. So our unit tangent is going to be exactly this vector, except I divide by this given speed at which you are driving your car. Okay. So it's a little messy, but not too bad. Let's take the derivative of this guy so we can get the direction of the turning. So the derivative of this guy. So the square root stuff isn't scary because they're just constant. So we're only taking the derivative of sine and cosine here. So the derivative is going to be this thing. And as far as the z coordinate goes, this is constant with respect to t. So the derivative is going to be 0 here. And let's compute the magnitude. Okay. Let's see. Again, if we factor out the constant, we just get cosine squared plus sine squared, which turns out to be 1. So we just have square root of r squared over r squared plus 1. And r, we could just take out r from the square root to just have r in the outside. And you think it's starting to get messy, but actually if we divide by this constant here, the constant in front of cosine and sine cancels out nicely. So our unit normal vector is just going to be negative cosine, negative sine, and 0. Okay. I didn't give myself enough room to compute the binormal, so let me squeeze in a new page. Okay. So let's see. To get the unit binormal, we're looking at the cross product. All right. So the unit tangent, let's see, it was, I think it was negative r sine t over square root of r squared plus 1. R cosine t over square root of r squared plus 1. And then 1 over square root of r squared plus 1. That was our unit tangent. And the unit normal was negative cosine t minus sine t, and then 0. Okay. All right. So now let's compute the cross product. Let's see. For the ith component, we get this term times 0, which is 0, minus sine t times this thing. So sine t over square root of r squared plus 1. That's the ith component. And then jth component is going to be this ugly thing times 0 minus negative cosine t times this thing. So we'll get cosine t over square root of r squared plus 1. In the jth direction. Okay. And then the kth component, I guess I do need more room. I need to go to the new line. Is going to be, let's see, this ugly thing times negative sine t. So there's two negative signs, so this will be positive sine squared. Okay. Minus negative cosine times this thing. So because we're subtracting a negative number, this becomes plus. Okay. All right, so let's see what simplifies. This becomes sine squared plus cosine squared. So all we are left with is by the coefficient of those guys. So finally, minus cosine. And then r over square root of r squared plus 1. Okay, so this is the unit binormal. Okay, so you can kind of see that these computation could get pretty messy. Let's return to the page we were at. Okay. All right, so that was the parking garage. So roughly speaking, the unit tangent was pointing in the direction of the headlights of the car, right? Just going up and around in the forward direction as you climb the parking garage. The unit normal was the direction you were turning. So it was actually pointing more towards the middle, I guess the center of the spiral, right? So he was pointing to the left from the perspective of the driver because he was turning left as he went up the ramp. And if you kind of imagine your right hand as the driver, sticking in the direction of the motion and curling it towards the direction of the driver turning, the thumbs up, that's the direction of the binormal. So maybe better to think about the binormal is in the direction of driver's head pointing up, right? So it's a little bit tilted backward because let's see, the driver is driving in an incline, so the head is tilted slightly backward as it climb upward. But that's the direction that the binormal is pointing towards. If this parking garage wrapped around in the right and upward motion, then the binormal would have pointed downward from the perspective of the driver. All right. So now I want to talk about curvature using this idea of local coordinates. So the curvature is how tightly the curve is turning. So if you kind of imagine, so this is a geometric definition of it. So as the curve is turning, what you could do is you could try to draw uh, the best approximating circle that just kisses the curve that where you're at. So let's say you're on this portion of the curve, and you try to approximate that curve on the place where you're at with a circle, and then the curvature is going to be 1 over the radius of that circle. So if the curvature is high, if the curvature is large, that means that the radius of the circle is very small, because the r has to be small to have large k here, or vice versa. So if the curvature is small, that means this approximating circle is big and has large radius. So if it has a large radius, that means it's turning gently. If it's a very tight, small circle, then you're turning very quickly as you go along the curve. Okay. And when you're talking about curvature, this is like a geometric thing. It doesn't really matter how quickly you draw through the curve, like how quickly the particle is moving across this curve. So you want to kind of account for it by the arc length. So, so how do you, what do I mean by that? So you can look at how the unit tangent is moving per unit length you traveled in the curve. Or if you just kind of rescale the speed, basically what you could do is you can compute the magnitude of how the unit tangent is changing and divide by the speed. So if you're traveling fast, you can account for it by dividing by that. Okay, so as you might imagine, this is a really messy thing to be able to compute, right? Because when you're computing unit tangent, basically you take a derivative and then you compute the magnitude and divide by it. So you're already dividing by square root of sum of squares. If it's something like helix, things cancel out nicely. So you divide by maybe a constant. But in any other case, what you're dividing by is not it's not a constant. It's still a function that involves division by square root of something. And then if you take the derivative of that, right, which you have to do to compute t prime, that involves a derivative. So you're probably using quotient rule. And then you have to use chain rule because there's probably something inside of the square root function. So it gets really messy very quickly. So this next theorem kind of helps you compute it in a much nicer way. So the curvature could be also computed. You still have to take derivative a couple times, but you just have to take the derivative of r twice, take the cross product, and find its magnitude. So I know cross product is a lot of work to compute, but it's actually way less computation than the formula I've given you just before. Let's first prove it, and then we'll try it out with a couple of examples. Okay, so how do I show that? Well, let's start with the definition of the unit tangent. So T is r prime divided by the magnitude of r prime. Because I'm going to do a lot of manipulation here, I'm just going to rewrite the magnitude of r prime. So this is a speed with a scalar function v. So I'm going to replace it here, and then I'm going to replace it back later. But it's going to save me a lot of writing to do that, so I'm going to do that. Okay, so this means that the unit tangent is r prime divided by the function v. But if you bring v to the left-hand side by multiplying both sides by v, here's what I get. So velocity is speed times the unit tangent, basically. Okay, from here, let's take the second derivative. So r double prime. To compute that, we could use the product rule. So we know that's true. Okay. So we take the derivative, and then we're gonna compute the numerator part here. So we already wrote down what r prime is. We know what r double prime looks like. So let's see what the cross product would look like. So this is the r prime. This is the r double prime. I can distribute this cross product to the two terms on the right-hand side. And remember that, so here's a fact that I'm going to pull out that I don't know if you remember or not. Okay. So the magnitude of the cross product is same thing as the magnitude of the two vectors involved times the sine of the angle in between. But if you look at the first term here, the directional vector is you're cross producting a vector to itself, right? It has a different scalar function in between, in front of it, but forget that part. Just the direction. These two are the same vectors, so that means the angle between this vector is 0, but sine of 0 is 0. So the first part of this cross product just happens to be 0. So we can just drop it from our formula. What we have left is just the function v times t prime. Okay, so v squared times t cross t prime. And again, I'm going to use this idea. Well, t and t prime, remember, is pointing in the direction of the unit normal. And unit normal vector is orthogonal to the unit tangent. So they're 90 degrees apart. So the sine of the 90 degrees, or sine of pi over 2 radian, is equal to 1. All right, so that's nice. So sine of theta is just 1. And, well, magnitude of unit tangent is just 1. So we're left with the magnitude of r prime cross r double prime is v of t squared and magnitude of t prime. Okay. Or if you divide both sides by v squared, we get the magnitude of t prime is r prime cross r double prime divided by, this is v squared, but v, let's say, what's the magnitude of r prime? So we have magnitude of r prime squared. We're just one step away. Now, we just have to divide by the magnitude of r prime again to get our curvature. So we have this thing, and we just divide by r prime again, and we get our formula for the curvature. which was the theorem right here. Okay, let's try using this formula. All right, so let's take a curve, t squared, t cubed. Okay, so we take a couple of derivatives. The first derivative looks like that. Second derivative looks like that. And I want to take the cross product, but here's a work-saving technique. If you only want to find a curvature at a particular time, what we could do is we could just plug in this t value before we do rest of the cross product and everything else. But we have to be careful here. I can't plug in 0 before I take the derivative, because if I plug in the value, I lose the information about the variable changing and so on. But after we take the derivative, once we get r prime and r double prime, we're allowed to plug in 0. So r prime at 0 is 1, 0, 0. R double prime at 0 is 0, 2, 0. Now this is a very simple vectors to take the cross product with. So 1, 0, 0, 0, 2, 0. And most of these are going to be zeros. So ith direction, it's going to be 0 minus 0. In the jth direction, it'll be 0 minus 0. And in the kth direction, we have 1 times 2 minus 0. So we just get 2k. And then, so to get the curvature, we need r prime cross r double prime divided by r prime cubed. Okay, so the magnitude of r prime cross r double primes, that's just 2, divided by magnitude of r prime is just 1, so 1 cubed. So the curvature is 2. Okay, so that's that one. Maybe I can compute the curvature of helix as well. Here, I'll do it for OT, but it'll turn out that the curvature is fixed constant the entire time. So let's keep computing. So the derivative is negative r sine t, r cosine t, h over 2 pi, r double prime, negative r cosine, negative r sine, and 0, because that's fixed constant with respect to t. And then let's compute, well, we have to compute the r magnitude of r prime. And you can kind of tell why I like this example of helix so much is because the sine squared plus cosine squared equals to 1 is a big help when it comes to simplifying. Okay, So this becomes just r squared plus h squared over 4 pi squared. All right, let's compute the cross product. I should give myself more room. Okay. Okay. Any kind of zero entry is a big help with cross product because it eliminates a couple of the terms. Okay. Let's see if I can squeeze the answer in here. All right, for ith component, actually, let me move this up. For the ith component, we'll get 0 minus this thing. So it'll be positive RH over 2 pi sine t. Okay. For the jth component, I get 0 minus this thing. So that's RH over 2 pi cosine t. For the kth component, we'll get r squared sine squared plus r squared cosine squared. So they turn out to be just r squared. All right. Okay, so now we want to compute the magnitude of this guy. So it's the square root of this thing squared plus this thing squared. Okay, and I'm just gonna write down the answer now because sine squared and cosine squared, that's what we get, right? We factor out the coefficient in front, and then the rest is going to be just 1 plus the square of this guy. So we get r to the 4th there. Okay. And then we divide by the magnitude of r prime cubed. So take this and raise it to the 3rd power. So our very messy answer is going to be all divided by square root, or I'm just going to say this thing to the 3/2 power. Okay. So actually, I think this will simplify, but I think I've spent enough time on this problem that I think I'm just going to end it here. So curvature can be computed for these helix. Okay, just one more thing I want to cover in this video, and that's the special case where you just want to find a curvature of a function, just a regular single variable function. So to do this, I just want to kind of derive the formula for it. So you can kind of imagine this is a two-dimensional like XY plane, the way we usually graph our single variable function. But you could have like a parametric equation kind of running through this the graph by setting the x component to be x or just t, and the y component is f of t. And I'm going to use this formula for the three dimensions, the formula that we just derived earlier. this thing. And the cross product only makes sense in 3 dimensions. So I'm just gonna tack on a third dimension by setting that z component to be 0. We could still do that and make sense of curvature in 2 dimensions by imagine everything that fits within xy plane. Okay, so let's take the derivative. So the derivative of t is just 1, and derivative of f is f prime, and derivative of 0 is 0. Take the second derivative. Derivative of 1 is 0, derivative of f prime is f double prime, and derivative of 0 is still 0. And then take the cross product. So cross product of 1 f prime, 0, and 0 f double prime, 0. So the ith component and jth component, when because of the zeros in the kth component, those will disappear. The only surviving term is going to be 1 times f double prime, and that goes in the z direction. Okay, so that makes computing the magnitude easy. So computing the magnitude is just absolute value of f double prime. And the magnitude of r prime is going to be 1 squared plus f prime squared instead of the square root. And if you plug it in, if you cube that, we get the formula for curvature for any function f. So it's absolute value of the f double prime divided by 1 plus first derivative squared to the 3/2 power. So it's funny looking formula, but if you just want the curvature on the graph of a function, this is how we can compute it. Okay, so because this is getting to be a longer video, I won't do an example, but I encourage you to try to compute the curvature for any t for the function e to the t. It's not too bad because the derivative is just e to the t. Try it out. Okay, this is where I want to end this video. I'll see you later.